Hello, this is Dr. Strickland. In this video, we will investigate plane polarized light and optical activity. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. So in order for two substances to be classified as different compounds, they have to have at least one different chemical or physical property. And enantiomers are compounds that have the most properties in common. And the reason is that they have the same molecular formula, same molar mass, the same connectivity, the same functional groups. This gives them the same intermolecular forces. And because they have the same intermolecular forces, they have the same melting point, boiling point, density, polarity, and solubility in different solvents. So it's hard to find something that's different, and then because of that, a way to separate them from each other. But they do have two things that are different. They have different interaction with plane polarized light, and this is the optical activity that we're going to talk about. And they have different interaction with other chiral substances, and this is something that we'll explore later on. All right, so the thing about chiral compounds in general is that they're optically active. And an optically active substance, either a compound or a mixture, will rotate the plane of polarized light some number of degrees clockwise or counterclockwise in an instrument called a polarimeter, which we'll take a look at in lab. An optically inactive substance will not. And so you can classify substances as optically active or optically inactive depending on how they act in a polarimeter. So optically active substances will have an optical rotation which is not 0 degrees. Optically inactive substances will have an optical rotation of exactly 0 degrees. So things that end up with an optical rotation is either plus or minus some number of degrees are a pure sample of a chiral compound or a mixture of enantiomers that's not 50-50 in its proportions. Optically inactive substances are a pure sample, of an achiral compound, a pure sample of a meso compound, which we'll talk about a little farther down the road, and a mixture of enantiomers that is a 50-50 mix, and that's called a racemic mixture. So the optical rotation of one enantiomer will have the same magnitude, that is number of degrees, as the other enantiomer, but it'll have the opposite sign because it rotates the plane polarized light in the opposite direction. So if you have a clockwise rotation in the polarimeter, then your optical rotation will have a positive sign, and these compounds are called dextrorotatory. And if you put it into the instrument and you get a counterclockwise rotation, then the measurement gets a negative sign, and these are called levorotatory. Now, optical rotation is what's measured, and that's represented by this alpha right here. But we really needed a way to standardize optical rotations because they were very dependent on the exact experimental conditions. So the temperature, the concentration, the path length, the exact wavelength of light that was used in the polarimeter. And so specific rotation was invented as a way to standardize optical rotations so that scientists in different labs can compare their results. Most, but not all, optical rotations are measured at 20 degrees Celsius using the D line of the sodium line spectrum. And so very often in these specific rotations, which is the optical rotation with the brackets, you'll have the temperature up here in the top right quadrant and a D that represents the D line of the sodium spectrum down here in the bottom right-hand quadrant. So over here you have these different variables defined. So we've got the measure, optical rotation in degrees. C is the concentration, which will be grams in 100 milliliters of solvent of solution, and L will be the path length in decimeters. And so now you need to remember how many decimeters are in a meter. So it's a good idea to go and look that up. All right. So that is the basic story on plane polarized light and optical activity. There's one last thing I want to show you before you go, and that is two figures from your text, which kind of show you what's going on inside a polarimeter. So with an achiral compound, here's the light source, the D line of the sodium spectrum coming from this light source. And so initially you have, let me back up. Initially you have every wavelength coming from your light source, but the polarimeter will filter out all except the D line of the sodium spectrum. And so this wavelength comes into contact with your sample in the tube, but because you have an achiral compound in here, nothing happens to this filtered out plane polarized light. Now, if you look at what happens with a chiral compound, same sort of thing, the light source, the polarizer that filters out all but one plane of polarized light. You can see when it comes into contact with a sample tube that has a chiral substance in it, then this plane starts to rotate. And the number of degrees and the direction that it rotates is characteristic of whatever it is that's in there. So we'll have a lot more to talk about with this, and we'll do some things with it in lab. But for now, that'll do it. So if you have any questions, please send them to me.